Perfect.
So I work for GMV. We're the sixth largest space company in Europe. We have presence throughout, Europe, America, South America, North America, and in Asia. We're headquartered in Spain, and I'm responsible for a lot of the communication stuff coming out of our German office and coming out of sort of the what we call services branch. So that is to say, what do we do? Why did we start working on this stuff? Is we do a lot of system engineering and architectural stuff for testbed development for uh, like agency driven missions for telecommunication missions. We have clients in public, private, etc. And we do a lot of work with human spaceflight. So we come very much from the heritage traditional CCSTS driven space community. And with that in mind, I can't see who all's in the room. I'm going to warn you in advance. I am going to rag on CCSTS somewhat in this presentation. So for the people who will be responsive for that, me ragging on that, I'll see you at the next CCSTS meeting. Right now, the space industry is really undergoing a shift. We're seeing individual large agency driven flagship type missions to these bigger, cheap CubeSat, small sat constellations. We're seeing rooms full of people doing centralized operations, going into kind of very distributed, highly automated, sort of follow the sun type operations in some cases. And we're seeing, as I said, agencies and nation states going to corporate users. It's been a dramatic change even in the last 5-10 years in the amount of data that's being provided by industry in support of governmental tasks versus the historical way we've done that, which is the other way around. You see a lot of that, especially now in things like the war in Ukraine, et cetera. So the entire industry is changing directions. That being said, what that means for us as communication people is we wind up with more data from more sources going to more destinations with less oversight and with increased autonomy. And this seems like sort of a challenging order to get to solve until you recognize that somebody else has already solved this problem, and it's called the internet. The internet went from a pretty small, very well controlled cluster of PDPs to your light bulb having a pretty full IP stack, and it did it in 50 years. So by that metric, it is quite impressively quick how all this stuff happened. When you think about what the internet is, and you can think about this in whatever technical or governance oriented way you wish, it's a robust protocol stack. It has a concept of operations. It has a very low barrier of entry. The interfaces are pretty much well documented, and it scales, and it's billable per the second for the cloud folks. So what's stopping us from doing that in space? What stops us from having that sort of flexibility, or from literally just using terrestrial protocols and mission concepts? Is it that we're afraid that there isn't space heritage? We're afraid to fly something that hasn't already been flown? Is it the way our existing architecture works, or what? So what happens if we just fit internet concepts in? And when I say fit, I mean sometimes it's a complementary fit and sometimes it's shoehorning, and we just smash it in there. What we think, and this is sort of my long-term bet, in 5 years, this is either going to be very right or very wrong, is that this will kind of enable these 4 different prongs of like super scalable system architectures that support AI, support ML, protocols that support network automation and have like protocol level intelligence, can make like what we would now have in something like BGP or routing level intelligence. From a data processing, increase throughput, make it easier. And then finally, lights out operation. Everything is autonomous. This is my hope, and I really hope it pans out this way. So the first pillar of that, which of course I think is very comfortable to everybody in this room, is the solar system internet. And we all kind of know what the solar system internet is. We know about the interoperability, the use of the bundle protocol, all that. And so I'm not really going to cover that much. What I am going to cover, or what I am going to remind everyone to keep thinking about, is what happens and how much of the existing terrestrial internet concepts can we reuse going forward in the solar system internet. Um, Again, I know there are people in the room where we've had very long discussions about this and are in agreement. Hi, Rick. How are you doing? Um, and so I want to remind, as an underpinning thing to this, even if we're using something relatively novel like the bundle protocol, or we're using something that's kind of bespoke for space, can we govern it as if it was the internet? Can we use normal network management, et cetera, et cetera? Where are the challenges? What are the problems? So with that in mind, and of course, there are lots of protocols. We'll touch on some. So the first pillar is mission architectures or system architectures. What happens if we take these very protected, very controlled pieces of flight and ground segment software and just sort of turn them into something like you'd see on Amazon Web? This is based on a prototype which was done by GMV. And from a political and project standpoint, it took 2 developers 6 months to build this thing. And the tenet that we came in on was there's a huge amount of paperwork that goes into flying a payload. Doesn't matter if it's satellite payload or International Space Station or whatever. There's user training, there's CCSDS documents, there's mission-specific ICDs, there's tailoring documents for your monitoring and control system. There's a lot of paperwork. And there are people whose entire job it is to manage that paperwork. That was my job for a while. So what happens if we just get rid of all of that heritage? We just throw everything out. We use gRPC to exchange data between everything. We use protocol buffers as the fundamental unit of telemetry and telecommand and everything. So if it's not a protocol buffer message, it's a file. And then we use either IP or DTN for user communication. So we abstract everything from all of the complexity, and we basically put it behind a single gRPC interface. What actually happens is you provide the ICD to your payload developer. It's a bunch of protocol buffer files in a GitHub repository. They can build their mission out against it. The flight and ground segment also kind of uses a dog fooding approach and uses the same gRPC definitions as we're providing to the users. All telemetry and telecommand is provided as gRPC. And we took those protocol buffer, blocks, we stuck them together and we sent them in bundles to get from space to ground, which in this case was ISS. The benefits of this were all of our tooling was really quick. The runtime environment was Kubernetes. The testing environment was all I think Jenkins was what we were using in that one. The debugging environment was honestly pretty much Wireshark. And the development environment for our guys who were doing payload integration and testing new things was a series of Docker Compose file that spun up the whole thing. Most importantly about this, we parsed out all of the CCSDS packets. We parsed out all of this spacecraft data into kind of a user readable form. So instead of having to say, look from bit 7 to bit 13 for this piece of information, it was some field in some protocol buffer. And what that meant is that we could rapidly interface this, like the monitoring and control aspects of it, we could rapidly interface it with normal terrestrial stuff like Grafana. So we were monitoring our whole system, checking everything with Grafana, that kind of thing. It was very cool, very nice, and it is being reused. And credit where credit is due here. Some of these concepts are now being taken on into the CCSDS Cloud Data Delivery Working Group, which is doing a lot of stuff with protocol buffers and gRPC. Otherwise, then, when it comes to the next page of it, how do you get your data around? And I used to work in large agencies. We had massive networking capabilities. We needed it, but they were not terribly flexible. So we've also said, okay, what happens if you just make everything a software-defined network and you put your compute and your networking just close enough to each other that you don't really have to, or that your users don't really have to understand the network topology, and that your network guys don't really have to understand what your users want. You know, your users connect an ingress point. It's all routed around within the SDN world. It makes it to some virtualized function or something. This notion is already used heavily in telecoms. This notion is also starting to be used in space as we're getting to 5G NTN. So it's solid and it works. And actually, internal to GMV, all of our testing for our high-speed testing, it's just one big multi-hundred gigabit SDN, and everybody just assigns slices to themselves and does whatever they want. It works quite well as well. So moving on. Likewise, for a long time in software, particularly in flight segment or in space and in flight segment, there were a lot of discrete boxes and discrete functions that were assigned to an ASIC or an FPGA or something. So what happens if you take the massive amount of computing power we have, that GPUs and all this, and use that to just treat all the data you have like it's a normal packet? And you see this notion starting to pop up in the market segments that really care about low latency and high throughput. Guys like the quantitative easing folks, the quant guys, and high frequency trading do a lot of things like this. But they just kind of treat everything as a packet, and then they do processing on it as it traverses the network. So the first way we did this for terrestrial applications was we wrote something called Echidna a couple of years back. And that's been used now to kind of let us treat almost any space to ground or networking problem as a graph of modules with interfaces betwixt, and plug them in and basically build a Swiss Army knife. Most recently with that, we've built a CCSDS modem that goes all the way from IQ out to frames using pretty much nothing but standard C++, standard SIMD, fancy CPU instructions, and gRPC to control the whole thing. And it's running, as you can see in the screenshot here, at 170 megabits a second, which is actually a quite good rate for a fully software-defined modem. Otherwise, most of the time you start getting into GPUs or into FPGAs, both of which are applicable to these things. And if you look on board, especially in telecommunications, you spend a lot of time altering and modifying data as it traverses your space system, either because it's going from one antenna to another, or it's going through different parts of the bus and the components. And once again, the SDN people have had a solution for this. And it's the P4 programming language, which it's basically kind of a C/C++ hybrid that's designed for describing packet operations. And it's really good at describing packets. And it compiles out to either CPU code, FPGA, GPUs, et cetera, et cetera. So looking at like a pretty top of the line Xilinx FPGA now, you can define all of these packet transformations or all of this low level physical layer functionality in P4. And you can then drive, depending on the FPGA, 6 ports of 100 gig output, or 10 gig, et cetera, or 400 gig, all in a single chip. And there are rad hard reversals available. So we are moving in a direction where we have the computational resources. We can use terrestrial protocols, but at the expense of, I'm not going to lie and say that Versal's sip power. They're quite power hungry. They're quite hot. Um, but it's a possibility that's never been kind of made for us before. And so with that, what's next? We know these terrestrial concepts are applicable to the space internet. Everything is a packet. We can treat our satellites and our constellations as microservices or chunks of microservices or effectively a rack flying around. We just have to be considerate of delays. We have big hulking FPGAs. We have fast GPUs. We just have to be creative about it. And how that means to us from some applications is we have to be a little less tolerant or a little less demanding of requirements like jitter and requirements like exact end-to-end delivery times, because we can use COT stuff. It may be faster end-to-end, but it may not be quite as tuned for the space world. And how does that look going forward is in 5G, basically everything is a container. And your communication is all a bunch of stuff running on the network switch or in an SDN or both. Why not extend that to space? Do we get space routers? How far do we take this on? So, and with that, I open the floor to questions here. And yeah, thank you very much.